They never imagined that a single shell could slice through 12 inches of hardened steel like it was paper. It's 1943, somewhere in the North Atlantic, and a German Panther tank sits behind a ridge, its 75mm cannon aimed at an advancing Sherman. The American crew has no idea what's about to hit them. The Panther fires. The shell crosses 800 yards in less than 2 seconds. It doesn't just dent the Sherman's armor, it punches clean through the front plate, passes through the interior, exits the rear, and keeps going. Inside, the crew doesn't even have time to scream. The tank is dead before the sound of the impact reaches their ears. But here's the thing that haunted Allied tank crews for years. How did that shell do it? How did a piece of metal no bigger than a wine bottle cut through steel designed to stop it? The answer lies in a secret so brilliantly engineered, so devastatingly effective, that it changed warfare forever. And what you're about to discover will make you see every WW2 battle in a completely different light. Let's rewind to 1939, when the war was just beginning and nobody truly understood what was coming. Back then, tank armor was simple: thick slabs of steel bolted together. Engineers believed the thicker the armor, the safer the tank. But they were wrong. Because while they were building thicker walls, a small group of scientists and engineers in Germany, Britain, and America were working on something far more sinister. A shell that didn't need to be bigger or heavier to win. It just needed to be smarter. And that's where the real story begins. The problem was physics. When a regular explosive shell hit armor, it would explode on contact, creating a loud bang and maybe some dents, but rarely penetrating. Tankers knew this. They felt safe behind their steel walls. But then someone asked a dangerous question. What if we don't explode the shell on the outside? What if we make it go through first and then explode inside? That simple question led to the birth of the armor-piercing shell, and it changed everything. But making it work wasn't simple at all. In fact, it required solving a problem that seemed impossible. Imagine throwing a wine glass at a brick wall. It shatters instantly, right? Now imagine that same wine glass somehow passing through the wall without breaking. That's essentially what engineers needed to create. A shell hard enough to punch through steel, but not so brittle that it shattered on impact. The solution was in the metal itself. They discovered that by using specific alloys, combinations of tungsten, molybdenum, and chromium mixed with hardened steel, they could create a shell tip that was harder than the armor it was hitting. But hardness alone wasn't enough. The shell also needed weight, and lots of it, concentrated at the front. This is where the design became almost beautiful in its lethality. The shell was shaped like a teardrop, with all its mass pushed forward into a sharp, hardened point called the penetrator. Behind it was the shell body, and at the very back a small explosive charge. The entire thing was wrapped in a copper driving band that gripped the rifling inside the gun barrel, spinning the shell at thousands of rotations per minute as it flew through the air. That spin was crucial. It kept the shell stable, nose forward, like a deadly spinning top hurtling toward its target. And when it hit armor, something extraordinary happened. The moment of impact lasted less than 1,000th of a second, but in that microsecond, unimaginable forces were at play. The shell struck the armor at speeds exceeding 2,000 miles per hour, faster than a bullet from most rifles. The hardened tip concentrated all that energy into a tiny point, and the pressure was so immense that the steel armor didn't just crack, it flowed. Yes, flowed, like butter under a hot knife. The atoms in the steel couldn't move out of the way fast enough, so they were forced aside, creating a narrow channel through the armor plate. The shell pushed through, its body following the path carved by its tip, and emerged on the other side, still spinning, still intact, still deadly. And then, a split second later, the fuse triggered and the explosive charge detonated inside the tank. If you're fascinated by hidden WW2 secrets like this, make sure to like the video because what comes next gets even more intense. But here's the question that haunted engineers on both sides of the war. How do you make the fuse wait? If it triggered too early, the shell would explode outside the tank, wasting its power. If it triggered too late, it might pass completely through without exploding at all. The solution was a tiny mechanical marvel called a base detonating fuse, and it was positioned at the rear of the shell. This fuse was designed to withstand the enormous shock of impact, thousands of times the force of gravity, without triggering prematurely. It used a small inertial weight inside a spring-loaded mechanism. When the shell hit armor, the sudden deceleration as it punched through caused the weight to compress the spring just enough to arm the fuse. Then, once the shell was inside the target, the fuse would complete its trigger and detonate the explosive. The timing had to be perfect, measured in milliseconds, and somehow they made it work. Now imagine being inside a tank when one of these shells penetrated. First, you'd hear a sharp, metallic scream, the sound of the shell tearing through the armor. Then a blinding flash. The explosive detonating inside a confined space created a pressure wave so powerful it could rupture organs even if you weren't hit by shrapnel. But the shrapnel itself was the real killer. The shell casing fragmented into thousands of white-hot pieces of metal, ricochet around the interior at supersonic speeds. Anything in their path, flesh, bone, equipment, was shredded instantly. And if the shell hit an ammunition rack or fuel tank, the entire vehicle could erupt in a fireball seconds later. Tank crews called these penetrations catastrophic kills, and they were the most feared way to die in armored warfare. But what made these shells even more terrifying was that the technology kept evolving, getting deadlier, more precise, more unstoppable. By 1942, engineers realized they could make armor-piercing shells even more effective by adding a cap to the nose. This might sound counterintuitive. Why add material that could slow the shell down? But the cap served a brilliant purpose. When a shell hit sloped armor angled to deflect incoming fire, the sharp nose would sometimes glance off instead of penetrating. The cap, made of softer steel, would crush on impact, creating a flat surface that gripped the armor and prevented deflection, allowing the hardened penetrator underneath to bite in and punch through. They called it an armor-piercing capped shell, or APC, and it made sloped armor far less effective. But then they took it one step further. They added another layer, a ballistic cap on the very front, streamlined and aerodynamic. This didn't help with penetration at all. Instead, it reduced air resistance, allowing the shell to fly faster and farther with less drop. The final design was called Armor-Piercing Capped Ballistic Capped, or APCBC, and it was the ultimate evolution of the concept. These shells could hit targets over a mile away and still punch through thick armor. And if you want to discover more untold WW2 stories and deadly hidden technologies like this, subscribe now, because what you're about to see next will blow your mind. But while engineers were perfecting the shell itself, another group of scientists was working on something even more radical. They asked a different question. What if we made the penetrator even smaller and denser and fired it even faster? This led to the development of Subcaliber ammunition, and it changed the game completely. Instead of firing a large shell the same width as the gun barrel, they created a much smaller, extremely dense core, usually made of tungsten carbide, one of the hardest materials on Earth, and wrapped it in a lightweight sabot, a kind of shoe that fit the gun barrel. When fired, the sabot and core traveled down the barrel together. But the moment they left the muzzle, the sabot fell away, and the tiny tungsten core continued at incredible velocity, sometimes exceeding 3,500 miles per hour. The physics here were devastating. Because the core was so small and so fast, it concentrated immense kinetic energy into an even tinier point. The armor didn't flow anymore, it shattered. The core punched through like a needle through cloth, creating a narrow hole and sending a spray of molten metal and fragments into the tank interior. They called this ammunition armor-piercing composite rigid, or APCR, and later armor-piercing discarding sabot, or APDS. British tanks firing APDS rounds could penetrate German armor that had been thought invincible. But here's the catch. Tungsten was rare and expensive. Germany, surrounded and blockaded, couldn't get enough of it, so they had to be selective, saving their tungsten-cored rounds for the most critical moments, the most dangerous targets. And this is where the war became a chess match of engineering and desperation. When Germany couldn't get enough tungsten, they switched to steel cores and tried to compensate with higher velocities and better fuse design. When the Allies faced German Tigers and Panthers with armor too thick to penetrate, they developed new guns with longer barrels and higher muzzle velocities. Every innovation was met with a counter-innovation. Tank armor got thicker, so shells got faster. Armor got sloped, so shells got caps. It was an arms race measured in millimeters of penetration and inches of steel. But the real genius wasn't just in the shells themselves, it was in the tactics that evolved around them. Tank crews learned to aim for weak points, the turret ring, the lower front plate, the engine deck. They learned the exact ranges at which their shells could penetrate specific armor thicknesses. They memorized penetration tables, calculated angles, and waited for the perfect shot. A good gunner could hit a moving target at 1,000 yards and place the shell exactly where the armor was weakest. And when that shell hit, it wasn't just a mechanical failure, it was a psychological one. The crew of the target tank knew that if a shell penetrated, they had seconds at best to escape before the ammunition cooked off or the fire consumed them. Many didn't make it out. Now imagine the flip side, being the crew firing the shell. You're inside your own tank, the air thick with the smell of cordite and sweat. Your gunner peers through the gun sight, adjusting for range and wind. The loader slams a shell into the breech, a heavy metallic clang echoing in the cramped space. The commander gives the order, "You fire." The gun recoils violently, the entire tank rocking backward. Through the smoke and dust, you watch the tracer element in the shell base, a small glowing streak arcing toward the target. 2 seconds of flight, then impact. A flash on the enemy tank's hull. A pause. Did it penetrate? Then a secondary explosion. Flames erupt from the hatches. You penetrated. The enemy tank is dead. You reload and search for the next target, because in tank warfare, hesitation is death. But here's something most people don't know. Not all armor-piercing shells were designed to penetrate. Some were designed to do something far stranger and more terrifying. In the late stages of the war, engineers developed high-explosive anti-tank rounds, or HEAT, that didn't rely on kinetic energy at all. Instead, they used a shaped charge, an explosive with a conical cavity lined with copper. When detonated, the explosion focused into a jet of superheated gas and molten copper, traveling at over 15,000 miles per hour. This jet could punch through armor regardless of the shell's velocity, meaning even slow-moving projectiles or handheld weapons could destroy tanks. The shaped charge didn't melt through steel like butter, it burned through like a blowtorch cutting tissue paper. And unlike traditional armor-piercing shells, heat rounds were just as effective at close range as they were at distance, making them perfect for infantry anti-tank weapons. But back to the original armor-piercing shells, the ones that relied on pure speed and hardness, there's one more secret that made them so deadly. It wasn't just about penetrating the armor, it was about what happened after penetration. When a hardened steel shell punched through armor, it often created a phenomenon called spalling. The inside surface of the armor, under the immense stress of impact, would fracture and fragment, sending a shower of razor-sharp steel shards flying into the tank interior at lethal velocities. Even if the shell itself didn't explode, the spalling alone could kill the entire crew. Tank designers tried to counter this by adding spall liners, layers of fabric or soft metal on the interior walls, but they were only partially effective. The danger was always there. And then there were the stories. The tankers who survived penetrations described them in ways that stuck with you. One American Sherman commander recalled a German shell passing through his tank so fast it entered through the front, exited through the back, and he only realized they'd been hit when he saw daylight streaming through both holes. The shell never exploded, it just passed clean through, missing everyone inside by inches. He called it a miracle. Others weren't so lucky. A British tanker described the sound of a penetration as a crack like lightning striking inside a metal can, followed by a heat so intense it felt like the air itself was on fire. He escaped through the top hatch with burns covering his arms, the only survivor of his crew. These weren't just weapons, they were psychological terrors. Knowing that a shell could appear without warning, punch through your protection, and kill you before you even knew you were under fire, it took a special kind of courage to climb into a tank every day. And yet they did. Thousands of crews on all sides climbed into their steel coffins and went to war, trusting their armor and their guns to keep them alive. But here's the thing that ties it all together, the secret that makes this entire story so fascinating. The engineering inside these shells wasn't just about destruction, it was about precision. Every element, the alloy composition, the heat treatment, the fuse timing, the aerodynamic shaping, had to be perfect. A shell that was too hard would shatter, too soft, and it would deform and fail to penetrate. The fuse had to be tough enough to survive impact, but sensitive enough to trigger inside the target. The shell had to be balanced perfectly to fly straight over long distances. It was a marvel of metallurgy, chemistry, physics, and manufacturing, all compressed into a single projectile weighing maybe 15 pounds. And the factories that made them? They were pumping out millions of these shells, each one machined to tolerances measured in thousandths of an inch, each one heat-treated in massive furnaces, each one tested and inspected before being packed into crates and shipped to the front lines. The logistics alone were staggering. A single tank division could fire thousands of rounds in a major battle, and every one of those rounds had to be manufactured, transported, and supplied without fail. The war wasn't just fought by soldiers, it was fought by engineers, metallurgists, factory workers, and supply clerks, all working together to keep the shells coming. By the end of the war, armor-piercing technology had reached its peak. Shells could penetrate over 200 millimeters of armor at combat ranges. Tanks were being designed with composite armor, sloped plates, and spaced armor to try to defeat these penetrators, but the shells kept getting better. The Tiger II, one of the most heavily armored tanks ever built, could be penetrated by late-war Allied guns firing APDS rounds. Nothing was safe anymore. The age of invincible armor was over. Killed by a small group of engineers who figured out how to make metal flow like water under the right conditions. And that's the real legacy of the armor-piercing shell. It proved that in warfare, intelligence beats brute force. You didn't need a bigger tank or a bigger gun, you needed a smarter shell. You needed to understand materials, physics, and chemistry at a level that seems almost absurd for something designed to destroy. But that's what made it so effective. The engineers who designed these shells were solving problems that would challenge university physics departments. And they were doing it under wartime pressure, with limited resources, and with the knowledge that if they failed, soldiers would die. So the next time you see footage of WW2 tank battles, remember what's really happening. Those flashes on the armor aren't just explosions. They're the culmination of years of engineering, testing, and innovation. Every shell fired represents countless hours of work by people you'll never know, solving problems you'll never see, all to create a weapon that could punch through steel like it wasn't even there. And that's the secret engineering inside WW2 armor-piercing shells. A combination of hardened alloys, shaped penetrators, precisely timed fuses, and speeds that defied belief. They didn't just melt through steel like butter, they carved through it with surgical precision, turning the most heavily armored vehicles into death traps and changing the face of warfare forever. If you loved discovering the deadly secrets of WW2 weapons, make sure to subscribe. A new video revealing even more hidden truths is coming very soon, because there are still stories buried in history that most people will never hear, and you're going to want to see what comes next.